My name's Peter Khoury. I am head of wireless systems performance team at Ruckus. We're a small team. We have the aim to be mighty, a little bit like our business unit. I'm going to start with just a bunch of stuff that you already know. You probably already know that putting flows into the right access category and proper queuing makes a difference. What I'm going to do here, this slide, is just to kind of present that same data in a really interesting way, right? You might notice that the x-axis is logarithmic and the y-axis is logarithmic. That's because human perception of latency is on a logarithmic scale. So the difference between, say, 4 and 8 milliseconds of latency is similar to the difference of 20 and 40 milliseconds of latency. And different applications fall within those big kind of buckets of latency. Similarly, on the y-axis, we don't care so much about mean and median of latency. Those are the little circled spots here. Applications that care about latency really care about the latency of the outlier packets. So what you have here on the y-axis is 0.1, that's the 90th percentile of latency. 0.01, that's the 99th percentile of latency. And I flagged here the 95th percentile of latency. That's 1 in 20 packets in the voice flow is received. Oh, let me just describe kind of the scenario. What I have is I have 4 flows, downlink flows, going from the AP to the client. So there's a 4 megabit per second voice, 4 megabit per second video, 4 megabit per second best effort. And then I've also got a loading flow. This is a 20 megahertz channel, so there's a loading flow that's kind of saturating the link that's also best effort. So those 4 flows. The voice and video get great latency of 15 and 20 milliseconds. Not surprisingly, the best effort flow gets 66 milliseconds of latency, just because there's so much other traffic in that queue as well. So how did we get these results? We've got this product from Exensys, Byte Blower. It is traffic generator, but more importantly, it measures time very accurately. So the flows that we care about go out of the port, time-stamped out of the port, go through the AP, go over to the client, get bridged back into the switch. And we do that so that the same clock is used for sending and receiving the packet, so we can measure latency very accurately to like 1/10 of a millisecond. The flow that we don't care about as much, the load, the best effort load, just gets terminated at an endpoint on the client. And it is possible to measure the latency there, but these clocks aren't as well synchronized, so your latency measurements aren't that great there. So let's look at access categories in a representative application. Here we've got an iPhone doing FaceTime, and on the uplink, it's doing the right thing. It's putting packets into voice and video. Here you can see a voice packet. Here you can see video packets. The voice packet is small, the video packets are bigger. One thing to notice is that it doesn't mark the DSCP. So once the Wi-Fi header is stripped off and the packet goes over the wire, the receiving side has no idea that this is a higher priority packet. So when it gets to the AP and goes downlink, it just gets put into best effort, right? So these are the downlink packets that are just best effort packets. So now imagine I've got this FaceTime call set up, and I'm going to add a load to it, right? Well, so what does the load look like, right? Oh, shoot. Okay. How I'm going to do that here. So what I've got going on here, the FaceTime call that's on my laptop there is the one that's similar to the iPhone on the left. I'm going to add the load, and that we'll see what happens to that FaceTime call there. And what I'm going to do is I'm going to start traffic now. There we go. There. And you can see, all right, that's frozen and this isn't. And the FaceTime call is very... So no surprises, right? You knew that was going to happen. That's especially dramatic because it was a very, saturating the link, right? The same problem happens that I kind of showed with, say, gaming flows, right? The FaceTime traffic didn't mark DSCP, but let's assume there was an application that did actually mark DSCP. It goes up to the AP. That DSCP that has the priority goes through the internet, and then quite often the DSCP will just get bleached out. And still, same thing, just like Peter McKenzie kind of talked about earlier today with the VoIP phones, the downlink just is in best effort, right? So how do we solve this problem? Solve this problem. The first time that I ran into it, there was a client vendor came to us and wanted us to communicate to them, wanted us, the access point vendor, to communicate to them what we thought the wireless capacity was. And when we dug a little bit and asked them why, they said, oh, we're going to use that to drop packets in this process that's running on the client. So when they drop packets on the low priority flow, they're counting on the sender of that flow, the source of the flow, to ratchet back its throughput so that everything now falls within that estimated throughput that we give them. But of course, as a network administrator, as an access point provider, you're like, oh my God, I've just sent you packets that you've dropped in your client device. That is so bad. I was like, there's got to be a better way. So of course, I looked around, and the solution is actually really close at hand here. We're going to look at these flows again, and you've got these uplink flows in voice and video. And what we're going to do is we're just going to take that information on the uplink flows and look to see if there's any downlink flows that are the mirror image of that uplink flow. And of course, these green flows are that mirror image, right? So if we go forward, we can put that downlink flow in video and reprioritize it. So now what happens if we add a heavy load to flows that look like this, right? Like that. Okay. So here, I'll show you the video where I did this, and you'll see that I was pretty super excited. This is the proof of concept where I got it working. So here is a FaceTime call with video enabled, with QoS mirroring enabled. And what I'm going to do is I'm going to start the load. And you can see the FaceTime call still stays up. That picture over there is good. It's still responsive, everything is still copacetic. And I've got a decent amount of throughput, a decent amount of load on this. It's pretty sweet. Was pretty excited to get that working. You don't sacrifice, you're obviously going to sacrifice a little bit of the performance of this heavy load best effort stream, but not a lot. So let's look at how to actually make this work, right? One way to make it work is the Wi-Fi Alliance has a QoS Management R1 program. There are some test cases where the client sends a request to the AP, MSCS request to the AP to say, hey, I want you, AP, to mirror the flows that I send up to you, and the AP returns a response saying, yep, I can do that. No, I can't. There are clients that are, the Ruckus APs have implemented that. There are clients becoming available now on the market that implement that. Intel's latest BE driver does that. Their AX210 should do that. Just want to emphasize that this is not take the place, doesn't have to take the place of, say, application recognition. The two things can coexist. If you have application recognition and you want to prioritize traffic based on that, that takes higher priority than this does, right? This sort of provides a safety net and simplicity, It's simplicity. You just look at what the client does and you say, okay, we're going to mirror that, right? This is what the request looks like. Pretty simple. It's just a bitmap indicating what priorities you want to mirror. There's a limit if the client, for whatever reason, wants to cap the priority that comes, the downlink priority that comes back to it. That can be set in this user priority limit. Classifier mask is something that really doesn't change. That request can come either in an action frame or an association frame. The response, also super simple. Just it's like, hey, yep, we can do that. So that's one way of doing this. The other way of doing this is you just ask yourself, why do the clients actually have to make a request? Like, it seems inherently obvious that if the clients are correctly prioritizing the traffic, the AP just turns around and mirrors that traffic in response. So we have a mode of operation in Ruckus APs where we just mirror what the client does. You can turn that on and just start mirroring right now without having to wait for client software to make that happen. There's laptops, there's middleware on laptops. Intel and Dell both provide this that do a great job of picking the right applications and putting that traffic into the right priority for uplink so that the AP can mirror it. And downlink, Apple, you've already seen from FaceTime, does typically a pretty good job of sending their uplink traffic in the right priority access categories. So just to summarize, QoS Flex, super simple. It's a super simple safety net for real-time traffic. So thank you so much for your time.